Hello. In this video, I'm going to look at solutions of linear systems using the Gauss-Jordan method. So recall that we can consider a systems of equations with two unknowns, two equations. So the way in which that we can solve this, of course, is by echelon method, or even substitution method, or even elimination method. Now, the way of which that we're going to do this is by using what is called a augmented matrix. So we call this augmented matrix um, we call this augmented matrix where it's essentially the list of all of the coefficients of the system. So we use kind of like brackets to notate these, and we'll have like A, B, C, D, and then we'll go ahead and separate the coefficients with a vertical line. That vertical line is in place of the equal sign. So we have that this is K1 and that's K2, and that this is going to close. So this is going to be our augmented matrix. Now, the whole goal to solving a system is to reduce it. We want to reduce it to the following. We want to reduce it to where we're able to get the matrix in this form, where we have 1, 0, 0, 1, followed by a solution that we'll just call M, and a solution that we'll just call N. And then we'll just separate it like so. And then this gives us that the solution is that x equals to m and y equals to n. Now, interesting enough, what's happening is that these columns are kind of acting like the placeholders for the variable x and the variable y, and then we have our constants. Now, that's the same thing over here, where this is telling us that basically we have x equals to m and y equals to n. Now, the trick really is, like, how do we get from this matrix to this matrix? And that's using row operations. So, the steps of which that we can use is that the first is that we can actually switch rows. The second is that we can multiply a row by a non-zero constant. Now, the last step that we can use for our row operations is the following. We can multiply a row by a non-zero constant and add to another row. Okay, now traditionally the way of which that we can actually notate this is the following. So like if I take row I can actually switch it with row j. If I multiply a row by a constant, I can say like c times row I. That gives us a new row I. And then notice that this says that we can take any row, multiply it by a constant, and then add it to another row. And we can just call that row I. Now, I'm going to basically just put up a problem where I have the following. I have x plus 2y equals to 8, and then I have 2x plus 3y equals to 11. Now, I want to solve this system of equations by using these row operations. Okay, so what we'll do here is the first step that we need to do is to augment the system. So we know that we need to find the augmented matrix. So the augmented matrix is 1, 2, right, so we have 1, 2, 2, 3, and then we have 8 and 11. Okay, now we need to use these row operations. So the key is that we want to get this right here to be a 0. So we just think of, well, what row operation can I use such that when I add to here that gives me a 0? Well, minus 2 times row 1 plus row 2 to give us a new row, row 2. Now we can write that update over here. So we have 1, 2, 8, but then negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 plus 3 is negative 1. Negative 2 is going to be negative, well, it's going to be negative 16 plus 11 is negative 5. Now, basically, this is telling me that the next step that I need to do is to get this right here to be a positive 1. But the question is, how do I get that to be a positive 1? Well, we can actually just say minus 1 times row 2 to give us a new row 2. What does that do? Well, it gives us the following matrix. It gives us 1, 0, 1, 2, 8, and then we have 5. Now I want to find basically where I try to get this right here to be a 1, not a 1, a 0. So we'll just go ahead and say, well, we have that we need to make this a 0, so the only option that we might have is negative 2 times row 2 plus row 1, and that gives us a new row 1. Now, in this case, we have that this allows us 1, 0, 0, 1, followed by a 5, and then we have 2, negative 2 times 8 is negative 16 plus 5 is, let's see, actually it's negative 2 times 5, which is negative 10 plus 8 is negative 2. So here, this tells us that x is equal to negative 2 and that y is equal to positive 5. So that means that we have that the solution is negative 2 comma 5. Okay, so we have that this required what we call row operations. Now, this process is actually more specifically called the Gauss-Jordan method. So going from here to here, that's essentially what we call the Gauss-Jordan method by using these set of row operations. Now, similarly, if we were to consider, like, say, for example, a much larger system, like where we have perhaps like a1x plus a2y plus a3z is equal to k1, and then we have, like, let's say for example that we have b1x, c1x, b2y, c2y, and then let's say that we have b3z, and then we have plus c3z, and this equals to k3, and that's equal to k2. Well, similarly, I can actually do the exact same thing where I augment the matrix and I have a1, b1, c1, a2, b2, c2, a3, b3, and then I have C3, and then followed by we have these constants K1, K2, and K3. Now, of course, like if I'm going to augment and then use my row operations, basically I have that this is going to give me the following. It's going to give me 1 0 0 0 1 0, and then I have 0 0 1, followed by, well, this would give me the set solutions m, n, and then p. Now for this, we have that this gives us that the solutions are as follows: x equals to m, y equals to n, and then we have that z is equal to p. Now in this case, this is our solution. Now the thing of which that you must realize is that you have to get the matrix to go from here to here. So one way that we can look at this is that we have to kind of go like in a set order. Usually it's best to kind of work in columns, so that way we can kind of just work our way down and then go over. But you'll realize that some systems are different than the next. So that means that we will end up doing whichever method that we feel is most comfortable. So let's say that we have okay, so let's say that we wanted to solve x plus y plus z is equal to 2, and then we have 2x plus y minus z is equal to 2, and then we have 3x plus 9y plus 6z is equal to 3. Now in this case we can go ahead and figure out like what is the solution to this system of equations. So the first step that you would need to do is you would need to go ahead and augment the system. So we have that this system is going to be 1 2 3 1 1 9 1 negative 1, and then 6, and then followed by 2 2 3. Okay, now the key is that okay, we need to get this to be a 1, which it already is, followed by this to be a 0, that to be a 0, and so on. So what we can do instead is we can actually use multiple row operations. As long as they don't affect each other, then we should be fine. So we have negative 2 times row 1 plus row 2. That's going to give us a new row 2. And then we have negative 3 times row 1 plus row 3 to give us a new row 3. Now that's going to give us our new matrix essentially. So we have that this is going to be 1 1 1 2. Now that's going to be a 0 followed by another 0. Now we need to continue, and we have that if we go ahead and we add, we have negative 1. Why? Because negative 2 plus 1 is going to be negative 1. And then followed by negative 3, and then followed by negative 2. Now the next one is going to be 6, so we have 6, and then we have that this is going to be, let's see, negative 3, that's going to be a 3, and then we have minus 3. Now in this case, the next thing to do would be to get this to be a 0 and this to be a 0. It's really just preference though. If you want to go ahead and work like in a kind of like a circle sort of, but still kind of sweeping from left to right, we can kind of do something like that. Okay, now notice that that this is already 1 technically. So let's go and just say that we're going to take minus 1 times row 2, and we're just going to make it a new row 2. Then we're going to take 6 times row 2 plus row 3, and we're going to make that a new row 3. Now technically we should never do something like this in the calculator because it might not know what we mean. So we have 1, 1, 1, 2, 0, 1, 3, positive 2. Now this is going to be a 0, that's going to be a 0. And this is going to be 3 minus 18, which is negative 15. And then we have that this is going to be negative 15 also. Okay, so we have that this is going to be such that we can now solve for z. So notice that to solve for z, we just need to multiply by the negative reciprocal, which is 1/15, negative 1/15, times row 3 to give us a new row 3. Now, what's going to happen is that we're going to have the following matrix now. We're going to have 1, 0, 0, 1, 1, 0, 1, 3, 2, 1, and then we have this is 1 and this is a 2, and that's yeah, just wrote a little funny. Okay, now right now we do know that z is equal to 1, so in that case we could technically back substitute and then figure out what y is and so on. But let's go ahead and just continue this, where we'll just say, okay, well, let's do row 1 minus row 2 to give us a new row 1, and then let's do negative 3 times row 3 plus row 2 to give us a new row 2. Okay, well, what this is going to do is it's going to give us that the new matrix is going to be 1, 0, negative 2, and then we have that that's going to be 0. Okay, so we have that's going to be 0. This is going to be 0, 0, 1, 1, but then we have 0, 1, 0, and then followed by negative 1. So our answer is almost there, because now we can just go ahead and say that, well, all that we need to do here is just add such that we get this to be a 0, this negative 2 over here. So we can do that by going ahead and saying 2 times row 3 plus row 1, and that's going to give us a new row 1. Okay, so that's going to give us the following. It gives us 1, 0, 0, 0, 1, 0, 0, 0, 1, and then followed by, so that's going to be 1, that's negative 1, and then that's going to be a 2, because you have 2 times 1 is 2, plus that is going to be 2, sorry. So remember that these acted as placeholders, x, y, and z, and then we have our constant that we can just call b, for example. So that tells us that we have that the solution is that x equals to 2, y equals to negative 1, and z is equal to 1. Now, this is our solution. So we have that if we were to plug this in to our original equation, we have that it has to equal to 2, like for the first equation, because you have x plus y plus z equals to 2, which in this case it does, because 3 minus 1 is 2. Now, what you can do is probably try your own example. So go ahead and try the following system. So try 2x plus y plus z equals to 3. 3x plus, okay, negative 4y plus 2z equals to negative 7, and then x plus y plus z equals to 2. So it's actually very similar to the previous problem. But what I'll recommend that maybe that you do is that you try to solve it in a way that you don't really need to use the complete Gauss-Jordan method. Because like I mentioned, what you could do, for instance, let's say that your matrix was like this, where you had A, then you had a non-zero constant, followed by another constant, followed by a constant. But let's say that this was a 0, and that was a 0, this was a 0, and then you have that this is going to be, let's say, like a constant, and then you have another constant, and then you have another constant. So theoretically, this is going to be your matrix. So in this case, you could actually solve for z, then you can solve for y, then you can solve for x, and these are just those constants that you would just be having right here. Like if this said 2z equals to 8, then you know that z is equal to 4, and so on. But in reality, yes, it is true that this should be a 1, and that should be a 1. Like that's a 1, that's a 1, and that's a 1, which basically is the whole concept of echelon method. Okay, so if we can get it in this form, then theoretically we can actually cut down the number of steps, and that's including with higher systems like a 4 by 3, well, 4 by 5 maybe. Yeah, because you have that each augmented matrix does have a dimension, so this dimension is like a 3 by 4. Okay. Alright, so be sure that you do go through the process of knowing how to use Gauss-Jordan method, and the key really is, yes, of really just figuring out like how do you get ones and zeros. So you're either going to have to use like either where you look at the least common multiple, or if you force it to be a 1 from the very uppermost diagonal, that means that you're probably going to end up using fractions. Okay?